effective values. So I am going to attempt to draw an outlet. So an outlet here in the United States looks something like this. So if you were to crack open the faceplate of one of these guys and look at what was going on, you would see that there would be 3 wires. Since I can't draw a white wire here, we'll just talk about the other ones. Or well, we'll talk about all of them, but I'll draw the white one in red, okay? So there is what's called a hot wire. There is a ground wire. Not all outlets have a ground wire. And then there is a neutral wire. And when you plug something in, it is applying a voltage difference measured from the hot wire to the neutral wire. So in a standard AC system like our homes operate on, nothing is actually connected to ground. That ground connection is usually made outside of the house, and the neutral wire is tied to that. And there are very specific reasons and ways to do it that are all covered in what's called the National Electrical Code, which is well beyond the scope of this class. So I believe we talked about this before, but if we were to plug a multimeter in and measure what that voltage is, or actually, I don't want to say a multimeter, let's say an oscilloscope, we would see that the voltage that's being presented by that system would look something like this. 120 square root of 2 cosine 120 pi t plus some phase angle theta v volts. Okay. Now that is a lot of information, almost all of which is unimportant. A shorthand notation for that voltage would be V with a tilde over it, and I'm going to explain what that means in just a moment, is 120 angle theta V volts RMS. Okay. So if you ever hear somebody call this outlet giving you 120 volts, they are referring to the RMS value of the voltage. Okay. Excuse me, here in the States, we use 120 volts. In Europe, it's 130 volts RMS. In Japan, it's 100 volts RMS. Our value is measured at a linear frequency of 60 hertz. In Europe, it's 50 hertz. And in Japan, it is both 50 hertz and 60 hertz, depending on what side of the river you're on, because of how it was occupied after World War II. So there are a bunch of frequency conversion stations along the river that make the grid work on both sides of the river. So what we're going to be talking about today is how to convert time domain signals into their effective values and what that really means. Okay. So what an effective value is it's the DC value that delivers the exact same amount of power to a 1 ohm resistor. That's it. So we're just describing the AC voltage by a DC voltage that delivers the exact same amount of power. Okay. So we know that the average power for one of our AC systems is, let's say that we have a voltage source acting on a resistor. It would be 1 divided by the period multiplied by the integral over exactly 1 period of our voltage waveform squared divided by our resistor value with respect to time, where this guy right here is just the instantaneous power absorbed by a resistor. In a DC circuit, we know that the average power is simply the DC voltage squared divided by R. So what we're going to do is make these two equations equal and solve for that quantity VDC, which I'm going to call V effective. All right. So with a trivial amount of algebra, we would find, let's see, we'd have 1 over t integral from 0 to t of v squared over r dt is equal to vd squared over r. I'm going to call this VDC, the effective, actually. Multiplying through by r on both sides and solving gives us the effective is the square root of 1 over t integral over 1 period of the square of our voltage waveform with respect to time. So this method here, or this equation, gives us what's called the root mean square value of our periodic voltage waveform, because we are taking the square root of the arithmetic mean, or the average, of the square of the voltage signal, which is why it gives us RMS values, okay? We could do a very similar derivation for current, and what we would find is that the effective value for a current waveform, I effective, is equal to 1 over t integral over exactly 1 period of the square of the current. So it's literally the exact same equation, except that we put the current waveform in instead of the voltage waveform. Excuse me. So let's work a quick example problem on how to use this equation, because I'm going to ask you to do it on your exam. Let's say that I have the following waveform. So this is V of t. Here's my time axis. Excuse me. And I have a series of triangular waves having a maximum value of 10 volts. And each triangular wave takes, let's call it 4 seconds to rise before it falls back down, like so. We have a periodic waveform formed by a series of triangular pulses that fall off. If I wanted to apply my equation, I would take the square root of the period, right? Let me write down the equation here, and then we'll put it into use. So by inspection, what is the period of my waveform? 4 seconds. I will integrate from 0 to 4 seconds. What does my waveform look like? As a function of time, because I need to put v of t into my equation. So it's linear. It could be described in a y is equal to mx plus b format. 10 over 4 is b, so 2.5 volts per second multiplied by time. What's my intercept? 0. Square this guy. I'm taking the integral with respect to time. And let's see, so when I square 2.5, so that's going to give me 2.5 volts per second squared divided by 4 seconds here out underneath my square root sign. And I'm taking the integral of t squared with respect to t, which is going to be t cubed over 3, evaluated at 0 and 4 seconds. That went too far. And so I'll have 2.5 volts per second squared over 4 seconds multiplied by 4 seconds, excuse me, call this 12. I'm taking out that factor of 1/3. 4 seconds cubed minus 0 seconds cubed. And somebody tell me numerically what this should be. Should be 10 over the square root of 3, I believe. Excuse me, 4 cubed minus 0 cubed, but for that particular number, it wouldn't matter. You are correct that I did make a mistake there. It should have been 0 cubed. So I've already taken that factor of 3 and I've lumped it in with that 4 seconds, which is why we have 12 seconds in the denominator now. Pardon? 5.774 volts RMS. A more exact value would have been 10 over the square root of 3. Volts RMS for this particular guy. Anytime we have a triangular wave, it's actually just going to be the peak value divided by the square root of 3 gives us our RMS value. If we had a sinusoid, let's say that we have a current I of t that is Im cosine omega t plus some phase angle theta I amps. And we want to figure out what the RMS value for this guy is, right? We're dealing with sinusoidal circuit analysis, so figuring it, yes. Root mean squared. So we are taking the root of the mean of the square of the signal. So square root of the average value of the square of the signal. How is it already on page 6? Oh well. So if we have a sinusoidally varying current like this guy, and we want to use our equation, which, to refresh your memory, I effective is equal to the square root of 1 over t times the integral from 0 to t of I squared dt. We're going to need to know what our period is. Who among you can remember what the equation for the period of a sinusoidal function is, as related to omega? Pardon? So 2 pi f is omega, and 1 over f is capital T, so 2 pi over omega, right? Yeah. For any sinusoidal signal, that will be our period as a function of omega. And so if we put in our intentionally very generic sinusoid into this guy, what we're going to find is that 1 over t looks like omega over 2 pi. We're going to integrate from 0 to 2 pi over omega. And when we square this cosine function, we're going to use that trig identity that we used on Friday. So I'll write it down over here. Again, cosine angle 1 times cosine angle 2 is 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. And in this case, our angles are the same. So this is going to make it even easier. We'll wind up having 1/2 Im squared cosine of 0, which is 1, plus 1/2 Im squared cosine twice omega t plus twice theta I. We're integrating that guy with respect to time. I could break this up into 2 integrals, but I'm not going to. Let's talk about that second term there. Okay. So we have a sinusoidal function that is oscillating at a particular frequency, omega. The AC portion of this signal is oscillating at twice omega. So what that means is that we're going to be integrating this sinusoid bit over exactly 2 periods. Does that make sense to everybody? So omega, let's say omega has a period of 2 seconds. Something oscillating at twice the frequency would have a period of 1 second, right? So there are exactly 2 periods in that 2-second interval. So that's what we're doing here. We're integrating the sinusoidal signal over exactly 2 periods. So I'm going to draw it down here real quick just to make sure we're all on the same page. So we have something like this. Arbitrarily, I'm going to say that my phase angle is 0 because all that would do would just shift things. So this is 1/2 Im squared cosine twice omega t. T. It would look something. Didn't give myself enough room. So forth. Since we're integrating, I want this area plus this area plus this area plus this area, because that's exactly 2 cycles. What's my area under the curve over those 2 cycles? Exactly 0. Which means that this whole term goes away. And I can also notice here 1/2 Im squared is a constant. So I could pull that out of my integration. So I would have omega over 2 pi times 1/2 Im squared. And now I'm just integrating dt, or 1 with respect to time. So that's going to be the same as having t evaluated at 2 pi over omega and 0. And what I wind up having is that my effective value is simply the magnitude of my sinusoidal current divided by the square root of 2. What is interesting about this result is that it is independent of phase angle and it is independent of frequency, right? Nowhere does omega or theta I show up in our result. So for any sinusoidal current, we can get its effective value simply by dividing the magnitude by the square root of 2. Would this derivation change in any way, shape, or form if we had done it with a sinusoidal voltage? No, not at all. So sinusoidal voltage also has an effective value of exactly the amplitude divided by the square root of 2, right? So let's circle back around to this symbol that I used here at the beginning of this page, B with a squiggly tilde over, okay? That is what I'm using to represent what is called an RMS phasor, okay? So let's revisit phasors again. If we have a voltage waveform, V of t is equal to Vm cosine omega t plus theta v, or if we have a time domain current I of t as Im cosine omega t plus theta I. To get our phasor representation, we simply hold on to the magnitude and the phase angle. This is what we've been doing up to this point. So this is the frequency domain. Now let's go one step further and convert from the frequency domain to the RMS phasor domain. V with a squiggle over it, or I with a squiggle over it, will simply be Vm divided by the square root of 2, angle theta v, and our current will be Im divided by the square root of 2, angle theta I. So it is literally the exact same thing that we did in the frequency domain, except our magnitudes are divided by a factor of square root of 2. RMS phasor domain. All right, so yes, theta I. So the current will have a phase angle. Oh, I see what you mean. Yes, thank you. Okay, so current has a phase angle of theta I, voltage has a phase angle of theta V. All right, so what we're going to talk about now is what's called complex power, okay? This is going to be a bit of a weird thing to begin with, and it's going to seem like it's very complicated, okay? We are going to summarize things with a tool called a power triangle that will provide you with an easy graphical method to remember literally all of these relationships that we're about to discuss here, okay? So with that being said, let's get into complex power. All right. So complex power is a quantity that's used by power engineers to succinctly characterize the power absorbed by a given load in a sinusoidal steady state system. It is a very, very powerful quantity because it actually contains a whole lot of information, okay? So much so that you can completely characterize the electrical performance of that load just by knowing that one particular quantity, all right? So let's say that we have an impedance, ZL, where in this case, this is just referencing a generic load, all right? Our load has a phasor voltage V across it, and a phasor current I flowing through it, where V is made up of Vm angle theta V, and I is Im angle theta I. We could and will wind up using the RMS phasor domain. So I'm going to get those concepts again real quick. V phasor is equal to V over square root of 2, or Vm divided by the square root of 2 angle theta V. And similarly, the RMS phasor current I will just be our phasor current I divided by the square root of 2, or Im root 2 angle theta I. I don't know why I keep doing that. All right. Complex power S is defined as 1/2 V times I conjugate in the frequency domain, or simply the RMS phasor voltage times the RMS phasor current in the RMS phasor domain. All right. So we now have a simple relationship in the frequency domain, or the RMS phasor domain, where power is simply V times I, but there's a little caveat there because it winds up having a complex conjugate thrown in there as well. All right. So let's talk about why this is the case. All right. So if I have an RMS phasor voltage V and an RMS phasor current I, and I put these guys into this relationship, what I wind up getting is Vm over the square root of 2 multiplied by Im over the square root of 2 cosine theta V minus theta I plus J Vm over the square root of 2 Im over the square root of 2 sine theta V minus theta I. Oops. I express the result of that operation as a rectangular form complex number. Excuse me. I'm going to lump together those square root of 2's. So that would give me 1/2 Vm Im cosine theta V minus theta I plus J 1/2 Vm Im sine theta V minus theta I. What's the real part of this? We've seen it before. Yeah, what's the cosine part? What does it represent? Yes, but what is the DC contribution called for the instantaneous power? The average power. That is the exact average power that we came up with on Friday. All right. So this weird, funny operation that we have here returns us the average power without having to do a whole bunch of extra crazy stuff like we had to do on Friday. So that's pretty dang useful. Okay? But it also contains an imaginary component, which we are going to call the reactive power. Q. All right. So this is, so the real part of S is the average power. Average power is measured in watts. The imaginary part of S is what's called the reactive power. And it is measured in what are called volt amperes reactive. Dimensionally, a watt and a volt ampere reactive are the same thing because it's simply voltage times current. All right. We use the different unit to specify the type of power that we're talking about. Excuse me. All right. So let's talk about the difference between these two parts. Yes, sir. When I multiply 1 over square root of 2 times 1 over square root of 2, I get 1/2. Right? All right, so the average power represents the portion of the complex power that can be used to perform work. Right? So in a system, effectively, it's just telling you what the resistance is doing. That's it. That's what the average power does. Which is why when we talked about the average power for capacitors and inductors on Friday, wound out to be 0. The reactive power represents the portion of the complex power that continuously flows back and forth between the source and the load in a steady state sinusoidal system. Okay? It is due entirely to the presence of energy storage elements like capacitors and inductors. Okay? So when we graphed the instantaneous power absorbed by a capacitor and the instantaneous power absorbed by an inductor, we saw that it had 0 DC offset, and then exactly half the time the instantaneous power was positive, and exactly half the time the instantaneous power was negative, meaning that half the time the inductor or capacitor absorbed power, and the other half of the time the inductor or capacitor supplied power. This is just another way to represent that portion. Now, you may be asking yourself, what's so special about the reactive power, since it just gets ping-ponged back and forth between the source and the load in our system? Reactive power is temporary energy storage. It is why we don't have blackouts. Okay? So the last time that the Super Bowl was held in New Orleans, somewhere around 10 years ago or something like that, right? Who was the musical guest? Probably not what you would remember about a Super Bowl. It was Beyonce, right? Did anybody remember anything in particular about that halftime show? Lights went out. Exactly right. The lights went out. Okay. So reactive power is something that can be injected into the electrical grid in order to prevent a blackout. And it can be done very quickly and very efficiently because it's done using just those temporary energy storage elements, capacitors and inductors, all right? Some of the loads that we deal with on an everyday basis absorb reactive power, like induction motors are a classical absorber of reactive power. So for every one of, let's say, if we tried to turn on every one of those heat guns in the room at the same time, I'd be willing to bet we'd throw at least one breaker if we did it, okay? We could offset that by adding capacitance into the system to supply reactive power, to counteract the amount that the inductors have absorbed. That process is what's called power factor correction, and it's something that we're going to learn about on Wednesday, okay? So let's take a moment to, actually I need to introduce one other concept before we really get into power factor, okay? So we have the average power, which is simply the real part of the complex power. We have the reactive power, which is the imaginary part of the complex power. We also have what's called apparent power. And we get apparent power by looking at our complex power not as a rectangular form complex number, but as a polar form complex number, okay? So if we did this simple operation, V, our RMS phasor voltage V times RMS phasor current I conjugate, and expressed our result as a polar form complex number, what it would look like would be 1/2 VM times IM with an angle of theta V minus theta I. For this portion right here, the magnitude of the complex power is called the apparent power. Measured in volt amperes. If any of you have ever tried to buy a generator or an uninterruptible power supply or something like that for your home, I'd be willing to bet you it's rated in volt amperes and not watts. And then this guy on the right-hand side here, we're going to call theta S, and it is the power factor angle. Okay. So buried in this simple operation of multiplying two RMS phasor quantities together, an RMS phasor voltage and our RMS phasor current, we actually have average power, reactive power, apparent power, and the power factor angle all buried into that same operation. And we don't even have to do any work for it, because if we express our answer as a rectangular form complex number, we get average power and reactive power. If we express it as a polar form complex number, we get apparent power and power factor angle, right? So we have literally 5 different quantities thus far, all buried into the same very basic operation, just multiplication of 2 numbers, all right? So let's talk about power factor for a couple of minutes here, okay? Power factor, PF, is simply a measure of the electrical efficiency of a system. So what I mean by that is it is exactly the ratio of the average power, the average divided by the apparent power, magnitude of S. Mathematically, that is identical to the cosine theta S, our power factor angle, all right? So let me give you a more, probably easier to understand knowledge of what the power factor is. How many of you have ever had to pay an electricity bill other than me? All right. What you're paying for is the average power. It is what you, as a user, consume by running your refrigerator or something like that, or powering your television, okay? S, the apparent power here, is what your utility provides. In an ideal case, what you consume and what is provided to you are the same quantity. In a practical case, that is not so, okay? So the apparent power is what we use to design our systems, because it is a worst case scenario. It is simply the multiplication of the magnitude of the voltage times the magnitude of the current. There is no consideration taking for if things are in phase or out of phase or anything like that. It is literally the most amount of power that you could ever need for your system. That's what we use to design for, so that we do things safely, right? The average power usually is only a portion of that. So we pay for average power. The utility generates apparent power, okay? If that ratio is low, significantly less than 1, and by that I mean 2.5% less than 1, you might get a fine from the utility. Now, for a standard consumer, that will literally never happen. Let's talk about the different loads that you might have in your house. Think about the appliances and stuff like that you might have in a home. Start rattling off stuff. Refrigerator, okay. So a refrigerator contains a compressor, which is going to be an inductive load because it requires the use of an electrical motor. So that is going to have some reactive power portion of it, but it also contains lights, electronics, and all that kind of good stuff, which are all going to be purely resistive based. So overwhelmingly, your refrigerator, while it does have some small reactive portion to it, is going to look mostly resistive. What else might you have? Washer and dryer. Washing machine is going to be probably more inductive than resistive, right? Because it's got an agitator that spins and all that kind of good stuff. It does have some electronics as well. The dryer, though, is probably more resistive than it is reactive, because you have a heat bar on that literally its whole job is converting electrical energy into heat. That is 100% resistive. So that's going to push your power factor back up towards being mostly resistive. Your HVAC units are going to be some combination of resistive and inductive. All of your televisions, computers, and all that kind of stuff and lights are going to be purely resistive. The only other thing I can really think of would be like a microwave oven, which is going to be, it's going to have some reactance as well, but it's largely resistive. So for the average consumer, your power factor is probably pretty close to 99% or higher. Now let's think about an industrial consumer, like a manufacturing plant, where they use lots of conveyor belts and things like that to move things around their plant. They have very, very large scale HVAC systems and fans to keep their workers cool and all that kind of good stuff. We might find that they operate at a power factor that is significantly less than 1, all right? That's where power factor correction comes in. So effectively what's going on here is the utility company has to pay for the infrastructure to supply you the worst case scenario power, whether or not you use it or send most of it back to them, okay? That's why they fine you if it dips too low. You're costing them money because they have to use heavier gauge wires, which means it's more copper, which means it's more money to them. And they also have to figure out something to do with all of that extra power that they've provided. I read a news article recently that was very interesting because there was an aluminum manufacturing plant in Texas. Aluminum smelting uses what's called inductive heating. And so that is literally just a coil and you pass your metal through it, and it induces a current high enough through the metal that it causes it to melt into a big pool of molten metal and all that kind of stuff. When that plant went offline in the past 5 or 6 years, the problem is that all of the infrastructure and stuff like that, their generators were designed with that plant in mind. So what that small region of Texas did was court a bunch of Chinese Bitcoin farmers to come into the region and run Bitcoin mining operations to use all that excess power that they had the capability to generate, because it was actually cheaper to buy it in Texas than it was in China. So anyway, yes, inviting, yeah. All right. So we have these two relationships for power factor, okay? Average power divided by apparent power, and then it is literally just cosine theta s. Our power factor is classified as either a leading quantity or a lagging quantity, okay? So if, sorry, let's go too far. 0 degrees is less than theta s is less than 180 degrees, we say that our power factor is lagging. And if negative 180 degrees is less than theta s is less than 0 degrees, we say that our power factor is leading. I want to scroll up here for just a second so we can see what theta s is again. Theta s, our power factor angle, is simply theta v minus theta I, okay? That is the exact same thing as the angle of our impedance, or the impedance of our load, right? Impedance, by definition, is the ratio of phasor voltage to phasor current. Doesn't particularly matter if it's RMS phasor voltage and RMS phasor current, because those square root of 2 bits are going to cancel each other out. And so we'll see that we just have the magnitude of the voltage, angle theta v, divided by magnitude of the current, angle theta I, which gives us Vm over Im angle theta v minus theta I, okay? So we can say then, for positive theta s's, what type of load would that be considered? Would it be inductive or capacitive? Pardon? Inductive, right? So let's say that we have R plus J omega L, right? That would be some resistance with an inductance in there. That would be somewhere around here on our complex number plane, right? Where this is the real axis and this is the imaginary axis. That angle is positive. So anytime we see theta theta s being positive, we have an inductive system. Anytime we see theta s being negative, transversely, we must have a capacitive system, because we know that our impedance there should be R minus 1 over J omega, or excuse me, R minus J divided by omega C. I was mixing up my forms there. I apologize. So our power factor angle tells us a whole heck of a lot of information without actually knowing what's in the system at all, right? We know whether or not it's going to be leading or lagging. So we know whether or not it's going to be a capacitive load or an inductive load. We know how efficiently or inefficiently it operates, because the closer to 0 our angle is, the more efficient our system is. The further away from 0 it is, the less efficient our system is. Ian.
So we talked about like both being inductive or resistant and how would something capacitive effectively be providing power into the grid?
It does provide Complex power, yes, or specifically, specifically, it applies or supplies reactive power. And we'll get into those relationships in just a minute. So I have just hit you with a wild amount of information. And I see a lot of glazed over eyes and confused faces, which is perfectly reasonable. So now I want to introduce you to the concept called the power triangle, which literally relates all these things so that you don't have to remember crap, all right? So for a generic load, Z is equal to R plus JX, where we are assuming that the resistance is a positive quantity and the reactance X is a positive quantity. We could plot our complex power on a complex plane. So this is our real axis. This is our imaginary axis. And let's say that we have a complex power S, like so. The projection of S onto the real axis is our average power. The projection of S onto the imaginary axis is our reactive power. The length of S is our apparent power. And the angle formed by S and the real axis is our power factor triangle. All of these relationships are also summarized by this. Complex power is just the product of the RMS phasor voltage and the complex conjugate of the RMS phasor current, which is equal to the average power plus J reactive power, or the apparent power with an angle of the power factor angle. If you can do that trivial relationship, trivial mathematical operation there, you know everything there is to know about the power behavior of your load. You know the average power, reactive power, apparent power, power factor angle. You can tell whether or not it's a leading or lagging power factor. You know whether it's an inductive load, a capacitive load, a purely real load, a purely inductive load, all that kind of good stuff. You know about the efficiency of it. All of that is boiled down into that one very, very simple operation, which is just V times I conjugate. Okay. Now, we can develop some alternative relationships for things when we're dealing with specifically resistors and capacitors and all that kind of good stuff. All right. And this will be to help us understand or help us determine the complex power for things when we don't have an easy way to get lots of information about it. Okay. So these alternative relationships are all founded on the fact that Ohm's law is still a thing, even in the RMS phasor domain. Right? So we could say for a generic load, S is equal to V times I conjugate, which would be the same thing as I times Z times I conjugate. What is I times I conjugate? the magnitude of I squared. That would just be I effective squared times Z which is going to look like IRMS squared multiplied by the magnitude of Z times the angle of Z if we have an impedance given to us in polar form. And it's going to look like IRMS squared times R plus J IRMS squared times X if our impedance were given to us in a rectangular form. So we could actually see what the resistive losses of our system would be just by knowing what resistance our system has and things like that. We'd know the ohmic losses and we'd know whether we were transferring power, reactive power in or out pretty easily there. So if we only know the voltage, we could take our relationship V times I conjugate, and we would have V multiplied by V over Z conjugate, right? Just rearranging Ohm's law here. When I have V times V conjugate, this is obviously just then the effective value of the voltage squared. And down here, we're going to have Z conjugate. When I take the conjugate of a fraction, I conjugate both its numerator and its denominator. So for polar form impedances, this is going to look like VRMS squared divided by the magnitude of Z with an angle of theta Z. And for rectangular form complex numbers, this one gets ugly. VRMS squared over the magnitude of Z times R plus J VRMS squared divided by the magnitude of Z. Sorry, that should be squared there, and that should be squared there times X. All right. If we have a resistance, where R is positive and X is 0, the complex power absorbed by our resistor simply becomes the RMS current flowing through it squared times R, or the RMS voltage across it squared divided by R. We effectively get our simple DC relationships that we've been dealing with the entire year. Things work out pretty well there. So we can say that resistors absorb average power, right? Because there is no imaginary quantity in here at all. And both of these quantities will always be positive. So resistors absorb average power. For an inductor, or for a purely inductive load, where R is equal to 0 and X is greater than 0, we'll find that the complex power absorbed is J omega L times I RMS squared, or J VRMS squared divided by omega L. So we can see that the complex power is purely reactive, right? There is no real part whatsoever. And that is both of the representations will also always be positive. So inductors always absorb reactive power. And finally, for a purely capacitive load, where R is equal to 0 and X is less than 0, our complex power comes out to be negative J over I RMS squared divided by omega C, or negative J omega C E RMS squared. So again, we have purely reactive power. But this time, our quantity will always be negative, which means that capacitors supply reactive power. All right. So we have two options here, one of which I don't know whether or not you really consider an option. The printer in Nethkin Hall that I used to print out the in-class assignments literally got changed while I was in class right before this one. Like they switched out the printers, and so I no longer have the IP address, which means I couldn't print out the in-class assignment. So you all could print out the in-class assignment because it's available to you because there's a printer here, or we can work problems and all that kind of stuff together and call that the in-class assignment for the day. What do you want to do? You want to print stuff and work on it yourselves, or do you want me to work some problems and help demonstrate all these relationships and all that jazz? Work some problems. Okay, great. Fantastic. No, that's legit, okay? So, sure. All right. Let me fetch. Cheston, may I borrow your TI calculator for a little bit? All right. So this problem that I have written out here would be very representative of something I might ask you to do on an exam. Okay. Sure. Yeah. So let's say that I have the following circuit where I have phasor voltage Vs is equal to 120 square root of 2 angle 0 degrees volts. I have an impedance ZA. I have an impedance ZB. I have an impedance ZC. And over here on this side, I have a current that is, let's call it IS, is equal to 5 square root of 2, angle 45 degrees. Amps. Now, I'm going to define ZA, ZB, and ZC here in just a moment, but I want to point something out. On an exam, I wouldn't actually set up the problem like this. This voltage and this current is, for a complex power problem, let me rephrase that. I would not set the problem up like this. And what I mean by that is this voltage and this current are not RMS phasors. And I solve all of my RMS phasor or I do all of my complex power in the RMS frequency domain. The reason why I'm setting this problem up in this way is because the person that created your homework assignments can be a real jerk sometimes. If you do not see an RMS after the volts or an RMS after the amps, you are in the frequency domain, not the RMS phasor domain, and you will need to convert in order to get the correct answers. Okay, so I'm just trying to be very, very explicit about that because some of your homework problems play fast and loose with the quantities that they give you. And I'd like to save us both a whole lot of headache and a whole lot of emails and nip that in the bud. All right. So if you are not given volts RMS or amps RMS, you are not in the RMS frequency domain. All right, so let's say that ZA is 10 plus J8 ohms. Let's say that ZB is 12 minus J3 ohms. Let's say that ZC is 8 angle 30 degrees ohms. I want us to find PA, which is going to be the average power absorbed by element A. I want us to find the magnitude of SB. And so what that means is the apparent power absorbed by element B. And then I want us to find QC, the reactive power absorbed by element C. And finally, I want us to find PFS, the power factor at which the source supplies power. I'm going to write that one down. All right. Now on your exam, I wouldn't ask you for 4 quantities. I'd probably only ask you for 1 or 2 tops. So this is going to take a bit longer than it would on a test, but we'll talk our way through it, okay? I introduced you to a crap ton of extra quantities today. 100% understand that. The circuit analysis that we will apply to figure out these quantities is identical to everything that we've been doing. Nothing new has been added on that end, with the exception of now we have to divide the voltage by a square root of 2 and the current by a square root of 2 to give us RMS values. I feel like that's a pretty easy change over there, all right? So let's identify things that we might need to know here to determine these things, okay? So if we wanted to figure out the average power absorbed by element A, we might need to know voltage drop over element A or the current flowing through element A. That seems unreasonable. Is that any different from determining the power for anything else we've done in this class? We either need to know the voltage, the current, or both. We're going to need to know the same quantities over element B. Similarly, we're going to need to know the same quantities over element C. And because we want to find the power factor of our sources, we're going to need to know the voltage and currents flowing through those guys as well. So I'm going to call this guy VCS. Actually, I take that back because I want the power factor at which the sources are supplying power. I want the current, oh yeah, current flowing into the negative polarity terminal. That was correct. Sorry. And let's call this guy IVS. Okay. So these are all of the different possible quantities that I can need. I honestly don't need all of them because we have those alternative relationships that we can use for generic impedances and all that kind of good stuff. So really, I pretty much just need a voltage or a current for all of the impedances. And then I need specifically to know that current IVS and specifically that voltage VCS to determine the power factor at which my sources supply power.
Say the bottom ground, can you just have a one equation, no amount? Can you start out as current one?
So, yes. Is that the way that you want to work it?
That's how
Okay. No, it's not a bad way at all. Okay, so Cheston's suggestion is to do that nodal analysis in quotation marks where we only actually wind up having one unknown quantity. All right. So let me ask you guys before we approach this method, does anybody have any questions about it? Like, does anybody have any alternative suggestions or anything, or is anybody opposed to doing it this way? I think this is probably one of the fastest and easiest ways to do it. Okay. So I'm going to call that node at the bottom my ground. And I'm going to call that node there up at the top B, because that nodal voltage VB is the exact same thing as the voltage drop over my impedance ZB with respect to ground, right? Those literally represent the exact same quantity. So I'm going to use the same variable so that I'm not unnecessarily confusing things. So if I were to apply Kirchhoff's current law at that node, what would my equation look like? So to make it super duper obvious, I'm going to be adding this current flowing to the left, plus this current flowing down, plus this current flowing to the right together. My goal here is to get an equation in which VB is the only unknown quantity. So, Tyler, can I ask you a question? How would what would my current flowing to the left through impedance ZA be? So it'll be VB minus that voltage over on the left-hand side because the current is flowing from the right to the left through impedance ZA, right? So it should be the node at which the current starts, which is VB, minus the voltage at the node that it's flowing to, which is that voltage source. But we need to pay attention here, right? VB that I'm solving for is an RMS phasor quantity, and that voltage VS is not an RMS phasor quantity. So how do I fix that? Divide it by the square root of 2. So it's literally just going to be 120 angle 0 degrees instead. Divide it by ZA, which is 10 plus J8. That's my current flowing to the left. Nothing, hopefully nothing too wild or crazy there. Joy, what's my current flowing down through ZB going to be? VB divided by what? Yeah, ZB, that's it. Since I am trying to find an RMS phasor quantity, VB, I need to convert my voltage VS, which is just a phasor quantity because it's given in volts, to an RMS phasor. I did that by dividing the magnitude by the square root of 2. Correct. VRMS is a unit. All right. Ryder, what's my term to the for the current flowing through ZC going to be? Yes, but you're overthinking this. Okay, so this part is the trickiest part. All right. When we've done nodal analysis previously, we would have had to consider, I'm going to call this guy Vx, the nodal voltage at this node. So we would have said VB minus Vx over ZC, and then we would have wound up having to write a Kirchhoff's current law equation at node X. So we would have had 2 equations and 2 unknowns. I think we are at a point in this class where I can say, I don't need to do that because I know what the current flowing through that branch is because there's a current source there, right? So the current flowing to the right through ZC is just negative IS. So we can just call it that without having to introduce another unknown quantity into our system. Does that make sense to everybody? So that would be negative 5 angle 45 degrees amps RMS, and set this equal to 0. So we have one equation and only one unknown. So we're good to go on that end. So now we wind up having to do some algebra to solve this guy. So let's go ahead and throw that into the mix. We're going to have VB multiplied by a factor of 1 over 10 plus J8 plus 1 over 12 minus J3 is equal to 120 angle 0 degrees volts RMS divided by 10 plus J8 plus 5 angle 45 degrees amps RMS. And so VB will just be that 120 angle 0 degrees volts RMS. That looks too much like a 6 for my comfort. over 10 plus J8 ohms. Sorry. Plus 5 angle 45 degrees amps RMS divided by 1 over 10 plus J8 plus 1 over 12 minus J3 ohms. Let's throw that in our calculator. If I get, let me make sure. $77.917 with an angle of negative 0.238 degrees volts RMS. Anybody else get something similar? Justin. Oh, I should have a tilde over it. Thank you. Flat line is a phasor. The tilde is an RMS phasor. So now that we know VB, we were asked to calculate the apparent power absorbed by element B. That voltage is the only thing we need to know, right? So if we use our alternative relationship, that says SB is equal to VRMS squared over Z conjugate. And that would mean that we would have 77.917 volts RMS quantity squared divided by 12 plus J3 ohms. Which is equal to 476.161 minus J 119.040 volt amperes, or 490.816 angle negative 14.036 degrees volt amperes. Which of these four numbers that I've just written down am I actually looking for? That guy right there. The magnitude of the complex power in polar form is the apparent power that I was asked to find. All right. Anybody got any questions about the analysis that we did for that portion? Dr. Kronk hasn't asked me for it yet. So presently slim, I think I discussed this the other day. Generally speaking, I am opposed to you guys getting to use an equation sheet for any of your exams. That being said, I tend to fight back on this exam significantly less than the other exams. So if any of the other instructors ever suggest that you all get to use an equation sheet for this test, I will not stand in the way. So what needs to happen is that you need to tell your cohorts in the other classes to beg their professors. I know it's a thing, but I'm going to be consistently opposed to allowing you guys to make your life marginally easier in this class because I am a huge jerk. So. I make plenty enough money to purchase my own food. Thank you, though, Chester. No. Like I said, I will not stand in the way if another professor asks to allow all of the students to have an equation sheet. But I will not volunteer that for myself because I don't think you need one. So, anywho, how did the analysis for figuring out what complex power absorbed by element B feel? Anything wild or crazy here? I know like I said, we introduced a crap load of new relationships, but fundamentally, all we're doing today is just taking what we knew already and doing something like that. Nothing wild or crazy there, okay? All right, so which part do you want to tackle next? I would argue figuring out PA or QC from this point would be easy-ish to do. So we cannot use voltage division to figure out what VA is. And it's because our system doesn't contain impedances connected in series. Current division won't work because our system doesn't contain impedances in parallel. John. That's exactly right. So Kirchhoff's voltage law will get us VA now that we know VB in exactly one step. Okay. So we could say that this is a separate part of the problem. Negative VS plus VA plus VB is equal to 0, which means VS minus VB must be VA. The only thing we don't know in that simple equation. So VA is then going to be 120 angle 0 degrees volts RMS minus 77.917 angle negative 0.238 degrees volts RMS which I get to be 42, excuse me, 0.085 with an angle of 0.441 degrees volts RMS. And from that, the complex power absorbed by element A is just going to be 42.085 volts RMS squared divided by the conjugate of ZA, which is 10 minus J8. Which looks like 107.997 plus J 86.397 volt amperes, or 138.303 with an angle of 38.660, pardon me, degrees, volt amperes. So which part of this am I actually looking for? So let's look. PA is the average power, which is the real part. What's that guy? Regardless of what I'm asked for, I never actually calculate it directly. I always calculate the complex power and then take the part from that I need, so that I don't have to memorize a bunch of different equations and all that kind of crap. I literally just have that one single thing. So that's a fantastic question. The units for the average power would not be volt amperes. It would be watts, because we only want the average portion or the real portion. Fantastic question. I absolutely ask questions like that on the theory part of your exam. What's the units of apparent power? Volt amperes reactive. What's the units of, excuse me, the units of apparent power are volt amperes. The units of reactive power are volt amperes reactive. The units of average power are watts. Fantastic question. Something like that will 100% show up on your test. In fact, when I ask you to do these power calculations and all that kind of junk on your exam, the numerical answer is going to show up 3 times. The units is going to change for each of them. So it is fundamental that you understand what the difference in the units are here, okay? So I will repeat it. Average power is watts. Reactive power is volt amperes reactive. Apparent power is volt amperes. Yes, Drew. Right. So in circuits 2, we'll actually probably spend more time on this than we do here in circuits 1. Circuits 2 is really only covers 4 topics. I know that seems wildly unfair to all of you who are not going to take circuits 2 because we cover like 24 topics in this class. Although transient analysis takes 3 days and all that kind of stuff. But in circuits 2, we cover op amps again, but in much more detail. We cover transient analysis of second order circuits, so RLC circuits, such as building off what we did in this class for a couple of weeks. We do steady state sinusoidal analysis for a couple of weeks, and then we get into three-phase power. So we spend a lot more than a day going over this stuff. So we're just getting the very, very basic fundamentals here, because for whatever reason, this class goes at a breakneck speed where we don't really have a whole lot of time to explain a lot of things. So, well, it's better late than never. It will be useful since exam 3 does cover exam 1 materials. Let's circle back around to this problem. All right, so we've gotten the first part taken care of. We've gotten the second part taken care of. We are now interested in figuring out what the reactive power is in element C. Okay. Anybody have any thoughts? Benjamin. So for that to be true, they would have to be in parallel, and they are not in parallel. So no. All right, so Drew. Right, we can literally just use that directly, right? We have an alternative relationship that gives us the complex power if we know the current flowing through the impedance, and we know the current flowing through the impedance because it's given to us. We don't actually have to do any work other than performing that simple calculation at all. So S, excuse me, C is simply IRMS squared times ZC, where in this case, IRMS is the RMS current flowing through element ZC. So what is the RMS current flowing through element ZC, Skylar? Exactly right. We just throw away the square root of 2 part. So that's the RMS phasor. What's the magnitude of that? Just 5. So we'd have 5 amps RMS squared times, what was this, 8 angle 30 degrees? So I don't have to scroll up. Thank you. So that's going to look like 173.205 plus J 100 volt amperes, or 200 angle 30 degrees volt amperes. So which part am I looking for, Caleb? Let's scroll up and see. So for element C, I'm looking for Q. So Q is what? Is it the real part? Is it the reactive part? Is it the magnitude? The reactive or the imaginary part. Exactly right. So that means we're just looking for that guy. And the units would be volt amperes reactive, because that's what the units of reactive power is. Alan. VAR. So the units will be VARs. And for apparent power, it'll be VA or volt amperes, and for watts, it's a watt or W. Yep. All right. So figuring out what was going on with element C was the easiest of all of them. How can I scroll up here so we can look at the other 2 quantities that we need to figure out? All right. So I need to figure out what IVS is, and I need to figure out what VCS is. Anybody have any thoughts on those guys? Okay, so VB minus VC, except that we never technically figured out what VC was. We can get it with the information that we have, right? So let's do that one next, okay? So we can write a simple Kirchhoff's voltage law equation that says VB is equal to VC plus VCS. Which means that VCS is equal to VB minus VC. And now we need to figure out what VC is in terms of quantities that we actually know. So let's scroll up here real quick. So VC to me, with the positive polarity on the left, negative polarity on the right, would be ZC multiplied by negative IS. Except IS, it would be expressed as an RMS phasor. Does that make sense to everybody? So if VC is negative IS ZC, then that's going to be negative or minus negative, so plus IS times DC. So let's see. .917 angle negative 0.238 degrees volts RMS plus 5 angle 45 degrees amps RMS times 8 angle 30 degrees ohms looks like 96.226 with an angle of 23.463 degrees volts RMS. So the power factor at which my current source supplies power will simply be the cosine of the voltage drop, or excuse me, the cosine of the phase angle of the voltage, which in this case is 23.463 degrees, minus the phase angle of the current flowing into the negative polarity terminal of that voltage, which is just 45 degrees. That looks like 0.930. Will this power factor be leading or lagging? Why? Absolutely correct. That is literally all you need to know. 23.463 minus 45 degrees is obviously a negative number. Therefore, the power factor has to be leading. This is another thing that I'm going to do on your exam. If I ask you to calculate a power factor, the numerical answer, the correct numerical answer will show up twice. Once it'll say blah, blah, blah leading. The other time it will say blah, blah, blah lagging. The only thing you need to know is the sign of the angle to tell you which of those two options to choose. A leading power factor always has a negative angle. A lagging power factor always has a positive angle. Okay? So let's scroll up here. The last quantity that we're interested in is the current flowing through the voltage source. Sarah, do you have any thoughts on how we might figure that out? How about that table? Destiny, Tyler, Andrew, you guys confer. Based on all the quantities that we know, what would be the easiest way? that current IVS? Sure, that is definitely one way to do it. So it would actually be IB minus IS, right? The current flowing in has to equal the current flowing out. But I would argue that there's maybe a little bit. So we don't know what IB is off the top of our heads, right? We know what ZB is. So we would have to figure out what IB is and then add to that some other quantity. But I would argue that since we know what VA is, we could just divide VA by ZA and get that exact same current without making it more complicated. Does that make sense? So we're saying that IBS and IA represent the same quantity.
A loop.
So,
Put it in terms of current for the local source.
I mean, yes and no. The problem there is that you would still have to take the voltage drop over VB into account, which in no way, shape, or form depends on IA. Right? So, all right. So, IVS is going to be equal to VA divided by ZA. And where the heck did we find VA? 42.085. Angle 0.441 degrees. Amps RMS divided by 10 plus J8 ohms, I think. Let me scroll up and make sure I'm not mistaken. Thank you. Oh, you're right. Sorry, I'm getting ahead of myself. I get this to be 3.286 with an angle of negative 38.219 degrees. Amps RMS. From this, a power factor at which our voltage source supplies power is cosine of the phase angle of the voltage, which is 0 degrees, minus the phase angle of the current flowing into the negative polarity terminal, which is negative 38.219 degrees. Which I get to be 0.786. And is this phase, is this power factor going to be leading or lagging Stephanie? Pardon? I disagree. 0 minus negative means we will have a positive phase angle, right? Positive phase angles always have lagging power factors. All right. So I ran 3 minutes long, so I'll shut up in just a second. What we are going to cover on Wednesday will be a probably 30 minutes-ish lecture on power factor correction. And then it will be a lab where we will literally do power factor correction on a small inductive load, which will literally just be a resistor in series with an inductor, which is exactly what an inductive load is. I have Friday set aside for a review session. We're absolutely going to do that. But I would also like to do Monday before the exam as a review session as well. Does anybody have a problem with having 2 days to literally just ask questions and all that kind of good stuff? Awesome. All right. I will see you guys on Wednesday. Thank you for my patience, your patience, excuse me.